All right, this is AP Calculus with Sparks. This is day 43. We're going to talk about particle motion. So one of the things we need to make sure we know about particle motion is that these are things that are moving back and forth along the x-axis. So either horizontally along the x or vertically along the y. So we have functions that will describe the position, the velocity, or the acceleration. But the particle is not moving along the graph of the function. Super important to recognize that right there. All right, so we're going to talk about velocity and acceleration in terms of position. And we have two types of velocities and acceleration. We have average and we have instantaneous. All right, so let's define that. Average velocity on the interval a to b is just the slope formula for the position function. So if p of t equals position or displacement function, then the average velocity is equal to p of a minus p of b over a minus b, which you should recognize because we've been doing average slopes, the slopes of secant lines, using that. Instantaneous velocity at a point C, P of C is going to be the derivative, so P prime of C. So let's see an example. So if a particle's position is given by the function P of t equals e to the t sine t, where P of t is in centimeters, t in seconds, we have a couple questions on that. So the average velocity, and we have our interval 1 to 3, so the average velocity is going to be P of 1 minus P of 3 over 1 minus 3. You're going to want a calculator to calculate that because e to the 1 times sine of 1 isn't something that readily comes to mind for me. I'm going to go ahead and give you the answer. So P of 1 minus P of 3 is negative 0.547, and 1 minus 3 is negative 2, which is 0.274, and this is in centimeters per second. So if we want to know the instantaneous velocity, we want to know exactly how fast it's going at t equals 1.5, we're going to need to find the derivative. So P of t is e to the t sine t. P prime of t, product rule, we have two things being multiplied together, is going to be e to the t times the derivative of e to the t, which is just 1. Or chain rule rather, sine t plus the derivative of sine, which is cosine, times the first function e to the t. And now we're going to evaluate p prime at 1.5. So this is going to be e to the 1.5 times sine of 1.5 plus e to the 1.5 cosine 1.5, and you get your calculator out and you get that p of 1 prime of 1.5 is equal to 4.787, and again we are still in centimeters per second. So we can see that the average was 0.274, but halfway in between 1 and 3, well, I guess it's closer to 1 than it is 3, we end up with the instantaneous velocity being 4.7. So it's quite a big difference between the secant and the slope of the tangent, rather the slope of the secant compared to the slope of the tangent at 1.5. Although I've went ahead and said this a couple of times, we can go ahead and write it down. We need to make a connection between what we've already been doing and now what we're doing here. So how do we find the slope of the secant line? Slope of secant on the interval a to b is equal to a function evaluated at a b all over a minus b, and that is the same as p of a minus p of b over a minus b, which is equal to average velocity. I'll squish right in here that the I think I'm missing that n somewhere else. Instantaneous velocity p prime of c is equal to the slope of the tangent. Alright, so we talked about average and instantaneous velocity, but we can do the same thing with average and instantaneous acceleration. So average acceleration is going to be the velocity slope. So we have v of a minus v of b all over a minus b. V of t is equal to p prime of t. Might be worth saying. That's our velocity. And then the instantaneous acceleration is going to be v prime of t. So we have acceleration is equal to v prime, which is equal to p double prime. Alright, so let's put this into practice. We're going to take our same particle position function, p of t equals e to the t sine t, and we want to find the average acceleration. So we know p of t was equal to et sine t. Velocity of t is equal to p prime of t, and we already found that. That was e to the t sine t plus e to the t cosine t. And so we're going to use the velocity to find the average acceleration, which is going to be v of, what's our interval? Oh, 1 to 3. V of 1 minus v of 3 over 1 minus 3. So we're going to use this function in there. So we need v of 1 and v of 3, and we end up with negative 10.403. And this time we had centimeters per second, but then we divided it by seconds again. So we have centimeters per second squared. So instantaneous acceleration, well, acceleration of t is equal to v prime of t, which is equal to p double prime of t. So we need to find the second derivative of p. We already have the first derivative up here. So we need to find p double prime. So we're going to have product rule, and we've already done that one once. So we get e to the t sine t plus e to the t cosine t, and that is this part of it. Then we have to add to it e to the t cosine t. So we're going to have e to the t cosine t minus e to the t sine t, and that's the second part of that, which this is a little messy. We've got 2e to the t sine t plus e to the t cosine t minus e to the t sine t, and I can probably factor an e to the t out of that if I wanted to, but we're not too worried about simplifying the algebra because we're going to put this in our calculator and figure out what it looks like at t equals 1.5. So we want acceleration at 1.5, which if you plug it in for t all the way through, you should get out 0.634 centimeters per second, and again, we are squaring that. Alright, so you turn the page and we get this. So f of x corresponds with position or displacement. F prime of x is going to correspond with velocity. Velocity is speed with direction, which will be either positive or negative. And then we have f double prime of x, which corresponds with acceleration. So let's see how these things are all related. So if we have the velocity function, this is f prime of x. The position, the motion of the particle then, is f of x. And so this is the derivative. And we're going to explore what does the derivative say about the function. In this case, how exactly is it affecting the position, or what can we tell from the velocity function about the position of the particle? All right, so if the derivative is 0 or undefined, these are our critical points. So where we have maximum and minimums on a function. But this is where there is a possible place where the particle, which is just moving back and forth, back and forth, back and forth. So what the derivative is going to tell us when it's equal to 0 undefined and undefined is these places where maybe it's turning around. So possible places where particle is changing direction. Just like we had possible max or mins but had to test it, these are possible places where the particle is changing direction and we have to check it. So if the derivative is greater than 0, we would say that is where the function is increasing, which means particle is moving to the right because the x values are getting bigger, so it's increasing. If it's less than 0, then we know it's decreasing, which means particle is moving left. So we're talking about just y equals f of x functions. When it changes from positive to negative, changes from increasing to decreasing, increasing to decreasing, which means it goes from moving right to moving left. When it changes from negative to positive, we know it changes from decreasing to increasing, which means it changes from moving left to moving right. So we're going to do the same thing for acceleration and relate that to velocity. So this is f double prime of x, and velocity is our f of x, our speed function with direction. So when the acceleration is 0 or undefined, well, we have potential change in velocity. When acceleration is greater than 0, then the particle is speeding up. Velocity is increasing. When acceleration is less than 0, then the particle is slowing down and the velocity is decreasing. When it changes from positive to negative, well, it had to go through 0, so the potential change in velocity is now a change. And when it goes from positive to negative, changes from increasing to decreasing. So it was speeding up, and then now it's slowing down. It goes from negative to positive. It goes from decreasing, where it's slowing down, to increasing, where it's speeding up. So if you turn the page, you see this picture of this graph where we are looking at the position. This is its position. the function s of t. So they're leaving it general on purpose, but I want to go through it with some numbers just so I could hopefully explain when they take particle motion and how it's not traveling along that function, what that means. So I'm just going to call this 1, 2, 3, 4, 5, and then let's call that, I don't know, 5, 10, 8, 6, and this one up here is up at, I don't know, 15. Doesn't really matter as long as they're kind of relative to where they're at. So what this means is that the position at, this is time, 1 second, the particle is at 5. Let me pick a different color. Let's go with red. So at 1 second, it's at 5. So here over here, we just have just an x-axis, and we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So here's 0, 2, 3, 4, 5, 1, 2, 3, 4, 10, and there's 15. So at time equals 1, the particle is at 5. And at time equals 2, it has moved in this direction and gone all the way up to 10, right there. Then you can see it decreased and went back to 8. So then it goes back here to 8. So this is A, this is B, this is C, and then it continues moving backwards until it gets to 6. And at D, it changes direction again and turns around and goes back and ends up here at 15. So that's what it's doing. I didn't overlap the lines. I kind of spaced them out a little bit so I could draw them and you could see them. But from A to B, C, D, and then back out here to E, that was what the particle is doing. And that's what that function, the position function, is telling you, is just where it is along that number line in its journey. Alright, so now to answer the questions I really want us to answer with generic, so pretend we don't have any numbers there. At which point is the velocity equal to 0? Well, this is our position vector, or sorry, our position, function. And any place along here where the slope of the tangent line is equal to 0, that is where the velocity is equal to 0, because the velocity is our derivative function. So that's going to happen at B and D because we have to justify our answer, because V of t equals 0 and has a max or, and P of t, oh, we're talking about S, sorry, they changed it, and S of t has a max or a min. Next we're asked, where does acceleration equal 0? The acceleration, this is our F double prime, recall? So when, how can we tell when F double prime is equal to 0? Well, that would be when we have a point of inflection. So where does that look like that occurs? Looks like maybe C. If it has to be one of those, I would pick C. So A, acceleration equals 0 at C because there is a point of inflection. And that's how we know. Now we need to know, when is the velocity positive? So velocity is our first derivative. So when is the velocity positive? When the first derivative is positive, when the slope is positive. So it's positive. Well, it looks like this is going to keep doing that forever, so we could say from negative infinity, I suppose, but we're dealing with time. Let's start at 0. So it's going to be from 0 to where our maximum was, to B, and it's also from D to infinity, because at D it turns around again and is moving in the positive direction. And how do we know this? Because S of t is increasing. So this video is getting a little long, so you think about these. I'm going to go ahead and write the answers so you know what they are, and I bet you can get them all. All right, so take a look here, and this is what I have for the rest of these answers. I look forward to the next time around. See ya!